Well, welcome back, and we're halfway through the semester. Cheers, and hopefully the second half will be, yeah, it's gonna be quick. Time just flies. Well, exam 2 is online. You can see your graded paper, your score. Your bonus has been added to your score, and if you exceed 100%, I also add your bonus to your exam 1 score. There's nothing I want to talk about. I put the exam solutions online on Canvas. So you go ahead and check where you make mistakes. And if you would like to set up a time to talk with me or just drop by during the office hour to talk about your exams, I'm more than happy to do so. In general, I think everybody's doing pretty decent. We're doing a lot of computations for this exams, and everybody, I can see people did a lot of practice on this. So everybody actually, basically did fine on all the procedures, which is great. All right. Any questions regarding the homework and the exam questions? Or actually, let's save the exam questions for tomorrow. So you have a time to actually look for the solution yourself. Maybe you don't have to ask them. Mm-hmm. No question from homework? Projects or anything? All right. Let's go ahead and try to do chapter 4. Chapter 3 is done, basically. We did linear approximation. That's it. Okay, application of derivatives. We will talk about a lot of applications, but the main theme will be finding the maximum and the minimum value. Because it's closely related to something called optimization, which will be the last application we do. Okay. Well, what do you mean by that? It's pretty easy to understand. If you have a function, fx, assuming it's continuous, assuming we can find the information about all the derivatives, you certainly have the maximums and the minimums. For easy function, we can draw it. For harder function, we probably have to use everything we know about derivative, because you can see the minimum and the maximum, they all share the same thing. That is, your tangent line is horizontal here. So if you know the derivative, you will be able to find where they are, more or less. Okay. But why do we care? Because it's very important in real life. I can give you several examples. The first one is stocks. Everybody knows about this, right? You buy at the minimum. You sell at the maximum. In this way, you actually make the most money. And sadly, in real life, most people actually do the reverse. They buy at the maximum. They say, wow, Tesla is going great. I'm just going to wait until I cannot hold back. I'm going to buy it. And suddenly after you buy it, the whole thing drop. So you bought at maximum, and then you sell at minimum. You do it once, twice, 3 times. You find all your hard-earned money just went away. So you want to be smart about this. Second, let's think about something in chemistry or physics. Just say if you have some reactions, right? Nuclear reactions, whatever reactions, and you have the temperature or pressure going this way. What you want is you want to design a container. You say, hey, I want to buy a container. So I want to put all my reactions in this container. How strong should the container to be? Because I want the whole thing to be safe. Meanwhile, I don't want to spend too much money. Sounds good? How great is that if you can calculate before the reaction that the maximum is here, roughly like, I don't know, 200 kPa. And then what you can do is you just buy something 300 kPa, and you will say, well, that's going to be safe because it's even safe for the maximum. How about the rest? That's going to be good enough. Okay, things like that will be super useful if you know ahead of time. Number 3, of course, something called optimization in general. Okay. Basically, the framework is you have a limited resource. For example, of course, we go to the stupid building a fence thing, which you have seen probably for, I don't know, 100 times in your life. Just building a fence 400 feet. Okay, you want to build a rectangular fence. Okay, so this is what's going on. You want to use all the 400 feet. So you can do a square one, which a lot of people will do because it's beautiful. Or you can do a very clever one or stupid one, who knows, which is very long with 1 feet wide, 199 long, which is going to be a stupid fence if you just look at it. And you have all kinds of other ways to build this. Sounds good. The question is, with all these kind of ways of building the same fence with the same number of 400 feet, how do you construct the whole thing such that you can maximize the area it covered? Okay, you can see if you fence everything this way, that's 400. You cover 100 times 100, which is 10,000 square feet, let's say. Okay, but if you cover everything this way, which is still 400 feet, you cover 1 times 199, which is 199 square feet. So you can see, compared to the two different ways of fencing, this one is way bigger. This one is 50 times bigger. Okay, sounds good. So with the same resource, how can you allocate them in a clever way such that to maximize or minimize a certain thing? In this way, you save the labor, you save the cost, or you maximize the profit. By the way, what do you think will be the best way to fence a rectangular thing? The square is always the best. Sounds good? Later we will show why this is true, which is pretty easy to think about. But now, if I ask a second question, what if you can do a triangle? Or even a circle? 400 feet fence. Is triangle better than rectangle? Is circle better than rectangle? What's the best shape? Is the best shape this? 400 feet, but somehow, okay, it's the best. Think about it. Okay, that will be really interesting. Another thing you can think about is this, right? Let's say you have a farm and you're the only one who works on the farm. Let's say 100 acre. Okay. If you're the only one, you're not using the maximum potential of the farm because you can only farm maybe 5 acre or something like that. Good so far. So if you have one more person, what's going to happen? The production just doubled. Still okay? You have one more person, the thing got tripled. The more people you hire, the more production you have. Make sense to everybody? However, up to a certain point, what happened? You already reached the maximum capacity of the acre. For example, you have 100 people working on 100 acre. Now hiring one more farmer is actually going to cost you more in terms of labor compared to the additional production they can add to the acre. Does it make sense here? Okay, so if you think about, this is the people you hire. You can hire 1, 2, 3, 4, 5, 6, 7, all the way to 10,000 people or infinity people, okay? And this will be the profit of farming. At first, you hire a person, you double the profit. You hire, you keep hiring, this thing goes up. Still okay? As this thing goes up to a certain threshold, what happens? What happens is every one more person you add, they produce less. However, you still pay the same cost. Good so far? So that thing is going to actually grow slower. Up to a certain point, now you're at the maximum. Adding one more person, you don't even have a job for him to do. So you add 0 value. However, you still have cost. Still okay? So eventually this thing is going to drop. The more people you hire, let's imagine you hire infinitely many people. How many can they produce? Well, a certain amount, but you're going to pay negative infinity for the cost. So eventually this one goes forever down to the negative infinity part. Sounds good? So how do you maximize your profit? You want to hire this much people. Period. Okay, where is that? Okay, that we will use calculus to find the maximum and the minimum. Make sense here? Okay, what about adding a machine to your factory? What about buying one more car for your delivery route? Does it add value? Does it reduce value? Is the value added worth it due to the cost of adding more people, benefits, all the kind of stuff? So optimization is actually used everywhere if you want to start a company. I give you $100,000. Say, go ahead and start a delivery company or something like that. Well, how can you use this money for? You can use it to buy cars. You can use it to buy good cars. Okay, you can use it to buy Prius to save gas, or you can buy big trucks, which can deliver more but consume more gas. You can use it to hire people. You can assign 3 people per card, 2 people per card, 6 people per card. Okay, you can use it to do advertisement on audio, on the radios, maybe TV advertisement. You can use that to buy office. Make sense so far? You have all this kind of way to spend your money, but what's the best way to spend your money such that your profit is maximized, or such that the satisfaction of your customer is maximized, or the satisfaction of your employee is maximized, or the 3 of the things are balanced? Make sense so far? That is called optimization. You have a goal. Okay, you want to maximize it. And what's your freedom? Your freedom is you can allocate the resource whichever way you want. Sounds good? Think about even a bigger scope. What do you have for what's going on in the United States right now? Well, we do have a target. That is our economy. Which is measured by GDP, unemployment rate, and all the stuff. If we spend our budget of the government, we can make this one goes up. Sounds good. Meanwhile, we have COVID-19. If we spend money here, we can save people's life. But the economy goes down. Still okay? Do you realize how you spend your money really depends on which goal are you trying to optimize? It's this, or both to a certain extent. Half, 0.3, 0.7 distribution. Okay, so running a country is nothing but an optimization problem, except you probably don't have such a simplified goal because there are so many goals you need to balance. Okay, same thing works for robotics. If you just say, robots, please go ahead and optimize the safety of human being. Sounds like a pretty good thing to do, right? And in order to make you safe, the robot just decided it's better you don't move, then you're ultimately safe. Sounds good? And you said safe, you didn't say happy, right? Okay, so what I can do is I can actually, I'm gonna cut your arms and cut your foot and put you into a container. And you're alive all the time. Maybe you can be alive for 300 years. Okay, but clearly that is a bad goal. Okay, so think about it. It's a pretty interesting thing. Of course, for mathematics, we don't care about which goal you set. We just say, if you set that goal, how do we maximize it? And maybe the machine will come to a conclusion. Calculus will come to a conclusion that is the best way to keep people safe is stop them from moving. Okay, that's brutal, but that's what mathematics do. It's cold and brutal. That's why we say science cannot answer all the questions. You know, you need humanity. You need everything in human science. Science cannot tell you which one is better. It only tells you, which one is more efficient. All right. With that in mind, we go into the first elementary one, maximum and minimum. We're talking about a single variable, continuous, differentiable, so it's a very easy case. In general, it's going to be difficult, but we start from the basics. Okay. Number one, we want to define what we mean by maximum and minimum. We call them extreme values. Certainly you have 2 types. Okay. Now here is the careful mathematical definition. Let's see. B, a number in the domain D. Okay. Then FC is the absolute maximum of F on D if FC is bigger or equal than Fx for all x in D. Very easy to understand. If you have some function, you have a domain, let's say an interval. Something is called the absolute maximum on this thing simply because it's bigger or equal than everybody else in the domain. So that's what we mean by maximum. Sounds good? Several key points. Number one, you need a domain D. For example, if I say, hey, if I want you to build the most profitable company, I give you a $100,000 budget limit. That means I give you an interval. You cannot exceed that. Make sense so far? It usually doesn't make sense to say, hey, go ahead and build the most profitable company. We say, yeah, how much money do I have? As many as you want. No domain. Then of course I just pay myself. I make money. If I don't worry about cost, right? Okay. So usually you have a limitation. Second, this is so simple. Why do we want a mathematical definition to make it precise? Well, it helps you to clarify several things. Number one, can we have multiple absolute maximum, which means more than one? Can we? Well, let's take a thing. On 0 to, I don't know, 100, you will have a lot of peaks there. From 0 to 100, is it a domain? Yes. Is this one bigger or equal than everybody else? Yes, then this is the absolute maximum. Good so far. Is this a maximum? Is it bigger than everybody else and possibly equal? Yes, so this is also absolute maximum. Can you see that by a definition of bigger or equal, you can actually have as many as you want. Okay, so you can have more than one for sure. Number two, is this one a maximum? Absolute maximum. Everything is horizontal. Again, by definition, is this one bigger or equal than everybody else? Yes, and in this case, it's equal. Equal qualifies for bigger or equal than. Make sense so far? So even though the whole thing is horizontal, this is a maximum. Actually, everybody on this line is an absolute maximum for everything in the domain. So even for some easy case, in normal sense, it makes sense, but actually by mathematical definition, you make it more clear. Okay, then number two, we just need to have the same definition for absolute minimum if it is less or equal than for all x in D. Okay. What this implies is basically, maybe the way to optimize your profit is not unique. 3 farmer, 2 cars, and five employee and 1 car may give you the same profit. That's because you have two same absolute maximum. It's possible. Okay. All right. Second, how do we find the extreme values? To make it more precise, if I give you something, this is a function. How do you find the maximum minimum? Basically, that's what we're trying to ask. Okay. Now we have done this multiple times before. Hopefully you already developed those kind of warning sign in your mind. That is, before you go ahead and find derivative, is this one differentiable? Before you go ahead and try to find the limit, does the limit even exist? So before you go ahead and try to find extreme value, ask yourself, how can I guarantee that I can find one? Otherwise, I'm wasting my time. Make sense so far? That is called the extreme value theorem, which tells you when can you do it. Okay. If f is continuous on a closed interval, AB, then f attains its extreme value on AB. In another word, before you do anything, check if it's continuous and if it's on a closed interval. If not, you may not have an extreme value. Sounds good? Ask yourself, why? Why do we require it's continuous? That must mean if it's not continuous, there's no guarantee you can find a maximum or minimum. You may, but not always. Okay? Can you imagine? Not continuous means we have a hole, we have a jump, and we have an asymptote. Okay. If some of this case happens, you don't have a maximum. Can you see that? Do you have a maximum? Where is it? Here? There are certainly some point is higher, right? Okay, so where is the maximum? It's here. However, this point is removed. That means you have a biggest bar, you just can never touch that bar. So you don't have an absolute maximum. Make sense so far? Similarly for minimum, well, what if it's like this? Then no minimum. Okay. Second, what if you have something like this? Okay. What's the maximum on this interval AB? Infinity, or equal to, say, no maximum. Okay. That's why we need it to be continuous. Otherwise, bad things happen. Okay. That also means if I try to maximize my profit in this restriction, people actually tells you, you actually don't have a maximum. Why? Because you don't have an upper limit. You can make as much money as you want. Still okay? That's a good thing. That's a very good sign. That means don't even worry about the resource. You can be as rich as you want. In real life, this rarely happens. Okay. Same thing with if you're trying to build a chemical container and that thing has a maximum infinity, forget about it. Don't do it. It's never safe. Okay. Why do you want to close the interval? I think the idea is quite simple. just say you have AB, and you draw something like that, and you repeat what we just did. You either have a circle, or you have a asymptote. Okay. Is this one continuous on AB? Yes. The only thing goes wrong is actually at B, right? So I'm continuous on the whole open interval, but not the last point. However, the last point is the problem. Sounds good? All right, so next time if you see, please go ahead and try to find the extreme value. The first answer you have is, no, I can't always do it. However, if it's continuous, if it's closed interval, I can do it. Okay? That's the first one. All right, now second. Let's assume you already passed the extreme value theorem. You do have something which is continuous on a closed interval. Now, how do you go ahead and try to find all the extreme values, maximum and minimum? Well, all you need to do is just draw this closed interval and try to draw several examples. Okay. Where is the maximum and minimum? Here, maximum. Here, minimum, period. Okay. It is always the case that the maximum is always the last one or the first one? Not really. That can have something like this. Okay, where's the max? Where's the minimum? Make sense so far? You can draw several other cases. You will find, well, it's either one case or the other. Okay, as long as it's continuous, it all occurs like this. Then that gives us a hint. I don't know who is the maximum or minimum, but I do know who are the possible candidates. Okay, if it's this case, the candidates will be the ending points. Okay. If it's this case, the candidate will be this kind of point. We give it a name. We call it critical point. Sounds good? Now here's our statement. If we do have an absolute maximum or absolute minimum, they gotta be one of these. We just don't know which one. Still okay? So how do we know which one? Well, we do a third step, that is put them together and compare them. Whoever is the biggest, you are the maximum. Whoever is the smallest, you are the minimum, period. Sounds good? Okay, so we have the workflow now. Number one, when something comes in, check, can we do it? Extreme value theorem, continuous, closed. Great. Once we know we can do it, how do we find them? Well, we have a pool. That pool includes ending points, critical points. After I find all of them, there may be 12 points, or there may be 30 points, or 3 points, which are possible. Still okay? Finally, which one is the maximum? Which one is the minimum? Let's just calculate all of them, see the function value. Whoever has the biggest function value, you are the maximum. Whoever have the smallest function value, you are the minimum. Done. Is logic clear? All right. The only thing we're missing is we need to be careful about how to find critical points, because ending points are easy. You know the interval, you know the ending points. There are only 2. Okay. What do you mean by critical points? How do we find them? Okay. Number one, what do you mean by critical points? That's things like this. Okay. Why are they good candidates? Because they are technically a maximum. right? They are just may not be the absolute maximum because I can have multiple of these. Each one is a maximum, but it's not the maximum of everybody. It's only a maximum for a small period of time. Not all the time, but for a while. Make sense so far? Okay, for that reason, we give them a name. We call them local extremes, which means they're not the absolute extreme, but they're extreme for a small period of time. We have the local maximum. Let's talk about, let's see. Is a local maximum if okay, before for absolute, we need for or x in D, but we'll replace it by x near C. So you only work for a small group. Similarly, if FC is a local minimum, if FC is less or equal than fx for x near C. Same idea. Local maximum look like this. Local minimum look like this. The definition is very easy. Okay. Does it make sense in real life? Well, think about it. Let's say if you have 25 horses. Okay. You want to find the fastest horse. But you only have a track which can run 5 horses at a time. Is the setup okay so far? Okay. So what are you going to do? Well, you can run 5 horses at a time. You run 5 matches. Okay, each time 5 horse. So what you're going to get is you're going to have 5 champions, 5 fastest horse. Make sense so far? Are they the fastest of all the 25 horses? Of course not. Okay, but each one is the fastest of the local one, which are the 5 horse. This one is the fastest. These 5 horse, they are the fastest. Still okay? Now the question is, do you believe absolutely that the fastest horse will be one of these 5 winners? I don't know which one, and certainly 4 of them won't be. Okay, but the fastest out of 25 will be out of these 5 winners because at least they beat their local competitors. Sounds good? It's even possible the last horse in my second match is actually faster than the fastest horse in the first match. It's possible. But my fastest will be in one of the winners. Okay, so this idea, you use it all the time in your life. That's why we have all the Olympic games and everything. You guys compete in the United States, find a winner. You guys compete in China, you find a winner. You guys compete in Europe, you find a winner. Now 3 of you have a match. Whoever wins is the fastest person in the world. It's possible that the fastest person in China is actually slower than the worst player in the United States. That's possible. But the winner is going to be the winner. You can use the same way to find the slowest horse. you know, in the 5 matches. That's also possible. So it works both ways. Sounds good? All right. Now we know the definition of local maximum and local minimum. Yeah, that's a nice definition. How do we find them? How do you find where the function look like this? How do you find where the function look like this? How do you find where may have something look like this or that? Knowing that what we're going over is the application of derivatives. You use the derivative. Okay. What's special about the derivatives at here and here? It's horizontal. It has to be. Do you remember in your web work? You know how to do this? You just set f prime x equal to 0. You can find where the x are. So it will solve this. It will also solve this. They actually share the same thing. Sounds good? All right. Let's push a little bit further. Why a horizontal tangent line will give you the maximum or minimum? If you think about it, what do you mean by maximum? That means on the left, it was going up. On the right, it was going down. That's what we mean by you achieve the peak, right? If you on the left, you go up. On the right, you also go up. Certainly, you're not the peak. Sounds good? Okay. So that's where my derivative change from positive to negative. Or that's where my derivative change from negative to positive. That's what I call a local maximum or minimum. So how does derivative change from negative to positive? It goes through 0. That's how you change it. Right? Positive, negative, it goes through 0. That's why. So if you think a little bit further, what do you have for maximum or minimum? You really have a derivative graph. That is before I was decreasing, now I'm increasing. Right? That's where my maximum is. Before I was increasing, now I'm decreasing. So before I was positive, now I'm negative. That's where I have the maximum. That corresponds to these two cases. That's what's happening. Sounds good? So first case, to find the critical points, just do this. Okay, very good. Then you have the second case. Can you have something that is a local maximum, but your tangent line is not 0? It might take you a while, but this. Remember, we just assume fx is continuous. We didn't say it's differentiable, right? Do you agree this is a minimum locally and this is a local maximum? Do you agree? Okay. Do you agree it's not horizontal here? Actually, you don't even have a tangent line here. It's not differentiable. Still okay? However, you do have positive change to negative for changing rate and negative change to positive for changing rate. So you still have this thing here. It's just this time your derivative is like this. You went from negative to positive. You didn't pass 0. Why? Because you jumped. Right? Because you don't have a derivative here. So that gives us an indicator. This one may also be a critical point, which means where your derivative does not exist. There's no guarantee it's going to be like this, but it's possible. Does everything make sense so far? Now let's write it down. For critical points, we have 2 cases. Good news is they both look at f prime x. It either does not exist or it's 0. These two are possible. So we have a way to find the critical point. Do the derivative, find where it's 0. Done. Up to now, all the pieces are done. Now we just need to put them together into a coherent process. Okay. Question. If then, let's do C. C is either A, local maximum or minimum. True or false? Who think it's true? Just click yes. Who think it's false? Click no. And I think the reason for true is obvious, right? It's like, yeah, here are the cases. Take a look. It's true. We have 7 against 2. 7 against 2. So we've got 9 people listening. That's great. And 8, 9. Okay. 3, 10. All right. For the people who says true, I think, can I speak for you guys? It's basically just look at the graph, right? It's true, clearly. We just did it. Okay. For the people who say false, let me take a look. Nick Peterson, why do you think it's false?
I feel like you wouldn't ask us the question if it's true or false if there wasn't like.
So everything I say is basically false, right?
Seems a little bit too easy to be just true. Like you wouldn't ask us. So I'm not sure.
So I would say like that's more like a Sherlock Holmes way of answering questions. It's just like, it's suspicious, okay? And good. Anton, do you have a reason other than Dr. Chen is tricky?
Just one example that came to my mind would be f of x equals x cubed, where there's a horizontal line at 0, but...
Hold on. This one, okay, let's do it. F prime x is this. And it is 0 at x equals 0.
Yes.
If this is true, that means we have a absolute, we have a local maximum or minimum at 0, right?
Mm-hmm.
But you have something like that. Is it a maximum or minimum?
Well,
Neither.
if you set the interval between like -1 and 1.
We're talking about local here, so we don't even need an interval.
Oh, okay.
We just say, hey, for a short period of time, it's neither. So this is false. Okay. And Nick, you got it right. That's a valid reason. By induction, though, not deduction. By the way, do you guys know the difference between induction and deduction? Okay, that's if you do science, you need to actually know the difference between these two. But let's finish this first. Okay, so think about this. How about we just cut this one and cut this one? Okay, I take the left of it, I take the right of it, and paste them together. Do you agree if I cut it from there, definitely they're horizontal, both left and right. But clearly this one is not a maximum or minimum. What do you think we should call this one? We call it a point. What's the name for that? be creative. When you see things like this, what do you want to do to it? Do you want to write on it? That's called saddle point. Okay. So the cool thing here is you may have a saddle point other than the local maximum or minimum, which is basically a local maximum and minimum half-half pasted together. It's up and up or down and down, so you can sit on it. Okay. When you go into 2-dimension, you will also have maximum and minimum, right? You can think about a bowl. That thing clearly have a minimum at the bottom, right? You can think about a hat. That is clearly have a maximum at the top, but you can also have a saddle, and in 2-dimension, that thing will look exactly like a saddle. Okay, so that's where the name comes from. Great. Deduction and induction. Every time you do something in science, you need to differentiate between deduction and induction. Mathematics is always deduction. Okay. A deduction thing looks like this. If A implies B and B implies C, then A implies C. That's purely starting from the start and use logic to actually derive new statements. So the new statement will always be true. Make sense so far? That's deduction. That's what we're trying to do with mathematics, physics. Induction works like this. All swans are white. Is it true? Mostly true. Why do you have that conclusion? Because I have seen millions of swans and they're all white. Therefore, I think all swans are white. You see the difference? The thing by induction can be possibly wrong. Why? That's simply because you collect your statement from evidence. Then a very possibility is that you haven't seen enough. Okay? Sadly, for a lot of things, especially in biology, we can only do induction because we don't know why the swans are white. We can only say, with all the people in the history of human, they probably observed billions of swans, and none of them reported a black swan. Therefore, all swans are white. Sounds good? So that's more like an induction. Okay. So back to the comment. Because Dr. Chen has always been tricky in this class, therefore, I'm going to assume he's a tricky person. And therefore, if he asks true or false, I answer false. That's purely by induction. By deduction, then it's harder because you need to prove I'm an evil person. Okay, not just by everything I observed about Dr. Chen so far is evil. Actually, he's an evil person, and somehow I can explain it. Then from now on, you can always answer false, and you will always be safe. If you don't have that, it's possible someday I give you something which is true. Okay, it's still possible. All right. Deduction, induction in mathematics. And this is more used in biology, I think. Just when people collect evidence, but a lot of evidence. Okay, and say this is the best we have so far. We cannot explain what's going on, but at least we can record what's going on. Bacteria, virus, whatever, right? Okay, at first when people see this, they may think this is not science, but actually this is science. Because there are some things which are difficult to study. Therefore, we can only rely on induction. It's not that we're cocky, like all humans are good because I have never seen an evil one. That sounds like a cocky conclusion, but actually, if you have millions of people doing the same experiment for several hundred of years, that's going to become the statement. Okay. All right, so let's write it down. Finding extreme values. Step 1, check extreme value theorem. If it passes, continue. If it doesn't pass, stop here. Refuse to do further. Second, if it passes, you find all your candidates, which you have 2 ending points, which are easy, A and B. critical points, which you find by doing this and doing this. After step 3, you have a pool of points. You may have 15 of them. You may have 2 of them, 5 of them, whatever. Compare all the points from 2. Whoever is the biggest, maximum. Whoever is the lowest, minimum. Is the logic clear? It may be still a lot of work to do. Still, it's better than nothing. For example, if I ask you when to buy the stocks, you say buy it at the minimum. Where is the minimum? Well, if you don't know this, you can check every single day, every single time. Now, at least you have probably 7 days to pick from. Okay, which is way better than anything is possible. Find extreme value. F on -2 and 1. Okay, keep in mind, this is something we don't know how to draw. Okay, but somehow we will know the maximum and the minimum. Number 1, check. Is this one continuous? Yes. Is it a closed interval? Yes, check. This one pass. Ending points. Well, -2, 1. Critical points. We need to check f prime x. Two case. Will there be any number if I plug in this? It will be does not exist. Not really. I don't divide by 0. There's no square root anything, so no point. Is there any number if I plug in my derivative become 0? Well, how about we solve it? Well, they may be a local maximum, maybe a minimum, maybe a saddle point. I don't know. One of these. Still okay? That's all. We have these 2 points. We have these 2 points. Together are 4 points. I know the fastest horse is going to be in them. I just need to check which one is. Okay, so number 3, check. What is f -2? What is f2? What is f -1? What is f 1/3? This is 1. Well, x cubed plus x squared minus x. So f -2, f1, f -1, All right, -1 and f1/3. (27, 3, 27, 9), so 1, 3, 9. Okay. So answer. Absolute maximum 1 at x equal to 1. Okay, I will just finish this. If you need to leave, feel free to leave. So you have two absolute maximums and an absolute minimum. -2 at x equals -2. Okay, so minimum, maximum.